The final type of intermolecular force that we need to learn about is called a hydrogen bond force. Hydrogen bond forces are not bonds, so I didn't invent the name, but I don't like that bond, so sometimes I'll just call them a hydrogen force. It is a very specific type of dipole-dipole intermolecular force and only exists between three substances. Those three substances are hydrogen fluoride, ammonia, and water. In each case, you will notice that hydrogen is bonded to an element that is in the second period on the periodic table. So oxygen, nitrogen, and fluorine are all small, and they all have a high electronegativity. And what happens is that because of that, you land up with a highly polar dipole. This is a strong dipole, and therefore your intermolecular forces are also strong.
Bonding is a strong dipole-dipole attraction between molecules in which hydrogen is bonded to highly electronegative atoms, such as oxygen, nitrogen, and fluorine. Water is an example of a substance where hydrogen bonding occurs. The highly electronegative oxygen atom draws electron density from the hydrogen atoms, giving oxygen a partial negative and hydrogen a partial positive charge. The attraction of opposite charges toward one another causes the hydrogen bond. In liquid water, the attractive force is transient. Water's relatively high boiling point is caused by this force. As water cools and molecular kinetic energy decreases, hydrogen-bonded clusters form. On continued cooling, these clusters of molecules form ice. Due to hydrogen bonding, depicted here by dotted lines, the structure of ice is less dense than that of liquid water.
Now, what happens as a result of this very strong intermolecular force is that instead of the trend that you would expect, if you look at the periodic table, look at group 4, you will see that it goes carbon, silicon, germanium, and tin. If you go down from tin hydride into germanium hydride, into silicon hydride, and down to carbon hydride, you find that your intermolecular forces get weaker and weaker because the molecules are getting smaller and smaller. Generally, small molecules have got weak intermolecular forces, whilst bigger molecules have got stronger intermolecular forces. However, hydrogen iodide has a higher boiling point than hydrogen bromide, which has a higher boiling point than hydrogen chloride, and then out of predictability, the hydrogen fluoride has a much higher boiling and melting point. The same is true when I take a look at the hydrides of group number 6. I can say hydrogen telluride, hydrogen seleniide, hydrogen sulfide, and water goes against the prediction. And I can also go antimony hydride, arsenic hydride, phosphorus hydride, and the ammonia goes out. So in other words, these three over here all behave out of the trend that one would normally expect of a small molecule. Generally speaking, small molecules have lower boiling points than big molecules. That is a general trend, but because of hydrogen bond forces, that does not happen with hydrogen fluoride, ammonia, and water.
Hydrogen bonding occurs when a hydrogen atom is bonded to a small, highly electronegative atom such as nitrogen, oxygen, or fluorine. In this example, its combination of high electronegativity and small radius enables fluorine to draw electron density away from the hydrogen atom. The HF bond is highly polar. Because hydrogen has no core electrons, its nucleus is left practically unshielded. This gives the hydrogen atom a relatively high partial positive charge, which is powerfully attracted to the partial negative charge on the fluorine atom of a neighboring HF molecule. Although hydrogen bonding is a type of dipole-dipole interaction, some hydrogen bonds more closely resemble ion dipole attractions in magnitude. In a series of similar compounds, such as these group 4A hydrides, boiling point typically decreases with decreasing molecular mass. This reflects the smaller London dispersion forces that exist between smaller molecules. Note, however, that in the series of group 6A hydrides, although the same boiling point trend is observed for the heaviest members of the series, the boiling point of water is anomalously high because more energy in the form of heat is required to break the hydrogen bonds and separate the molecules. The difference between the expected boiling point of water and its observed boiling point is due to hydrogen bonding.
So if we're going to summarize our intermolecular forces, we need to always consider the bond first. The bond has nothing to do with boiling points and melting points. Only intermolecular forces can be considered with boiling points and melting points. The bond, though, tells us something about the intermolecular force. So if I have a non-polar covalent bond, I will end up with a non-polar molecule. Generally, hydrogen phosphide is a slight example. The other time is that when my molecule is symmetrical, so the tetrahedral or the trigonal planar. And so, for example, if I had something like carbon tetrachloride, that would be a non-polar molecule, even though they're polar bonds, and it would also have an intermolecular force of London forces. London forces are super duper weak, and therefore they have very low melting and boiling points. The next one is, what if I have a polar covalent molecule? An example of a polar covalent molecule would be something like hydrogen chloride. And here I have a slightly negative side and a slightly positive side, and the dipoles are attracted to each other by dipole-dipole forces, and you get a higher, not very high, but a higher melting point and boiling point. When I put ions into solutions, such as sodium chloride into water, I will find that there will be an attraction between the ions and the polar molecule, which is dipole, and that doesn't have melting and boiling points so much because it is in the liquid phase and it is a solution. Then if I take a look at this weird circumstance, which is your NOF gases, nitrogen, hydrogen, and fluorine, nitrogen, oxygen, and fluorine, when they bond with hydrogen, we land up with hydrogen fluoride, water, and ammonia, and those are special types of dipoles which give me a very strong IMF, and the strong IMF is called a hydrogen force, and that causes a high boiling point and melting point. So let's try and predict the intermolecular forces between the following molecules. If I take methane, methane is a tetrahedral molecule. It has polar bonds, or not even really, it's a non-polar molecule. Any non-polar molecule will have London forces of intermolecular forces. Oxygen is O double bond O, that is again a non-polar, and again non-polar molecules are held together by London forces. If I take a look at something like ammonia, NH3, I land up with a polar molecule, and more than that, ammonia is one of my special ones. Remember, water, ammonia, and hydrogen fluoride have got hydrogen bond forces, hydrogen forces, and by the way, it is a polar molecule. Water is exactly the same. It is oxygen, and that's a polar molecule with hydrogen forces of attraction. Then if I look at something like carbon dioxide, we've drawn that out, C double bond O, that is a non-polar molecule. Non-polar molecules are held together by London forces. If I take a look at something like boron fluoride lands up with boron in the middle, and 3 fluorines coming off symmetrically, and you find that it is a non-polar molecule, and therefore it lands up that it is held together, since it is non-polar, by London intermolecular forces. If we take a look at something like hydrogen chloride, hydrogen is slightly positive, chlorine would be slightly negative because of the difference in electronegativity, and as a result you land up with a dipole. How does one dipole hold on to another dipole? With a dipole intermolecular force. And a dipole intermolecular force will be a stronger intermolecular force and will have higher melting and boiling points. What about carbon tetrachloride? Carbon in the middle, chlorine, polar bonds but a non-polar molecule, therefore held together by London forces.